Dr. Cotton. Our next speaker will be Dr. Anthony Lupo, and I'm bringing his... Dr. Lupo is an associate professor of atmospheric sciences in the Soil, Environmental, and Atmospheric Sciences Department at the University of Missouri-Columbia, and chairman and director of graduate studies for the department. His research has been in the areas of large-scale atmospheric dynamics, and climate change, and he has several peer-reviewed publications in each of these areas. He was a Fulbright scholar during the summer of 2004 to Russia, studying climate change at the Russian Academy of Sciences in Moscow. He has also served as an expert reviewer and contributing author to the Intergovernmental Panel on Climate Change assessment reports. Dr. Lupo.
Good afternoon. It's good to be here, and thank you for having me here to talk to you today. Today's the general outline of my paper as I talk about interannual temperature variations or some causes of these, and then I'll talk about some results from some areas for some research we did in our area in the Midwest USA, and I acknowledge Kevin Burke, whose master's thesis work we borrowed from some of this to do today. And interannual variability and climate change, I'm just going to show a simple model at the end. The Earth system is generally considered to be an externally forced system, all right? And of course, if you look at the Earth atmosphere system as a whole, we tend to break it down into several subparts, each of which exchange heat and mass with each other. And it's at these intersection points where they exchange heat and mass with each other that are some of the most difficult and vexing questions out there to be solved yet. For example, what I'm going to talk about now, a ocean and atmospheric interaction, an example of that, the El Nino, and it's not something that we have a trigger for, a triggering mechanism for yet. On the time scale of about 2 years to 9 years, which is about less than a decade, the dominant driver of the temperature variations in most places is the El Nino. This phenomenon's been known since the 80s, and of course, by science, and then of course, going back even further than that, Sir Gilbert Walker in the 20s, and it's been known by the Indians in the East Pacific since they've been there. But the El Nino is basically a warming of the waters of the East Pacific every 2 to 7 years, and its counterpart is La Nina, where you get a cooling of the waters in the tropical Pacific, which is thought to be a return to, quote, normal state. And then in the middle, you can define a neutral state. The El Nino cycle, again, has been well known for a long time, and what happens when the waters in the eastern Pacific warm is you change the heat distributions within the ocean and the atmosphere as well. And of course, by changing the heat distributions, you're going to change the mass distributions, which will impact the path of the jet stream and precipitating systems and things like that. If you look at temperature records at any location, these are monthly temperatures from about the mid-50s to the mid-2000s in a location in Missouri, and as you can see, the temperatures just go up and down every year, and you don't see much more than that, or you're hard-pressed to see much more than that. If you take and you convert this time series into wave space, just use an FFT, that's all it does is make that transformation. You see the annual cycle is fairly powerful if you plot this in terms of cycles per decade. And of course, you see some other peaks that rise above the dotted line, which represents the 95% significance level for a power spectrum. And of course, you can see periods in the temperature record now that are 3 and 4 cycles per decade, which is the time scale of the El Nino. I mentioned the El Nino today because we haven't had a strong one since the late 1990s, and it's kind of faded from the public's view. And of course, we know that in 2006 we had a very small one. The scientists know that, but the general public may not have even noticed it. But that was also predicted to be a super El Nino by some proponents of global warming, and it never materialized. The ENSO impacts the position of the jet stream, and I'm going to just show you this table of numbers that represents the occurrence of what we call blocking. Blocking is a phenomenon which represents a stationary ridging pattern in the jet stream that develops primarily over the oceans, over the Pacific and the Atlantic and Europe. Blocking is of interest to me because it's a phenomenon that's not been well forecast over the years by models or by operational scientists. And blocking as a ridge in the jet stream does what its name implies. It blocks the progression of the storm track. So if blocking events last for a month, they can have a significant impact on the weather of a region by keeping it very dry. Or if these blocking events last for an entire summer, as they did over Europe in 2003, producing very hot, dry conditions. Well, blocking, it turns out, is more prevalent in La Nina years than El Nino years or other years. And they tend to be a little stronger as well during those years. In the southern hemisphere, you get the exact opposite pattern. You get blocking to occur more frequently in El Nino years than any other year. El Nino impacts the strength of a lot of things. It has worldwide impacts. It has an impact on the strength of the Indian monsoon. This is why Sir Gilbert, or this was the the phenomenon that led Sir Gilbert Walker on his quest to discover why sometimes the Indian monsoon rains fail. And of course, it has an impact on hurricane frequencies in both the East Pacific and the West Atlantic. And we've done some studies in the China Sea and found some distinct impacts there as well. But this is so well known that Bill Gray uses ENSO state to predict the number of hurricanes in his model. And of course, all these have an impact on extreme weather in regions, whether it be hot spells, cold spells, rainy conditions, or whatnot. Here's a summary of the cause or the effects of El Nino worldwide. These cartoons are all over the internet, and you can find them anywhere. Again, during the warm episode or during El Nino, we tend to have warmer winters in the United States, especially across the northern tier, wet and cold in the south. During La Nina years, you get the opposite conditions, cooler conditions, especially in the north and northeast part of the country. But you can see impacts worldwide due to El Nino. There are other factors that may influence the strength of ENSO, and it's difficult to predict. I mean, there's been papers out that have shown that the polarity of Earth's magnetic field can impact the strength of El Nino. And lots of studies are out that show that this interannual variability can be tempered by even longer-term variability, such as the PDO or solar forcing. There's a reason why ENSO wasn't discovered until the 80s, and there's a reason why it's kind of dropped off the map now. Because we've discovered that during one phase of the PDO, well, we haven't discovered it, but we can show it in our region, that during one phase of the PDO, El Niños are distinctly weaker, and during the other phase, they're distinctly stronger. So here's our study region that we looked at, Midwestern USA. Remember, in that other diagram showed warmer than normal or warmer than typical conditions in this part of the country during ENSO, and cooler during this part of the country. And if you look at that and then divide that by PDO phase, PDO 1 in this case occurred from 1977 through about 2000, and PDO 2 was 1947 to 1977, and then again in the early 2000s. You can see that in Minneapolis, of course, again, very strong El Nino warm winters versus cooler winters and cooler years in the La Nina years. Very strong El Nino variability during PDO 1, very much weakened during PDO 2. The signal is much weaker. And in Fayetteville, Arkansas, you see a little bit of the opposite effect. El Nino winters, very cool. La Nina winters, warm. And the ENSO variability, not very great during either phase, although a slightly weaker during PDO 2 here. If you look at the differences between El Nino and La Nina winters in the United States, you can see that during El Nino winters, these warmer colors show up as higher pressure, which indicates warmer. This is going to indicate warmer conditions over the United States. The cooler conditions trapped off to the north. During a La Nina winter, a lot of higher pressure over Alaska, representative of that blocking that I talked about, much more blocking in this sector, and that contributes to colder conditions over the USA. All right, you can do a lot with El Nino and La Nina, and we just did a simple test here to show you that ENSO variability can be influential. Look at, there was a paper out recently by Zurita et al. That showed statistically that it's highly improbable that during the last 10 to 20 years, the global data set should contain the warmest, the warmest years. A lot of big deal has been made about this. And of course, if you look at what they did, they assumed first a stationary climate and then showed it was very highly improbable that the last few years should be the warmest ever. And then they tried using two autoregressive processes, one that represented long-term variability, the other short-term variability. So we had tried this in Kevin's work a long time ago, but we never added them together. But their conclusion was that it was indicative that global warming was here because the probability was very low that nature would produce such a series of warm years toward the end of our observed data set. And we just used a simple model to try to model US or global temperatures. Take your pick because they look pretty similar. And then we just took three functions and added them together to demonstrate that the latest years can easily be the warmest in a data set just by pure accident of the observation record. If you just take, we don't invoke any statistics here, and we don't even claim that we're going to try to physically explain global or US temperature records. We're just trying to show that we can demonstrate that you can get the warmest years at the end of a data set fairly easily. And here's the global temperatures. You had a rise to the 1940s, a fall to the 70s, and then another rise. U.S. temperatures, again, show a similar thing. So, all right, take a forcing process. Maybe we're coming out of the ice age, something we haven't discovered yet. So we just imposed a linear trend of 2 units per 125 time units. Then I took a natural forcing 2, which is could be our Pacific decadal oscillation or Atlantic multi-decadal oscillation. Give it 2 humps, just like we saw through the 20th century. And I made the amplitude 1 here, just for no reason. There was no reason for that, just for demonstration purposes. Again, and then our natural forcing 3, our short-term variability, ENSO. And by taking all those forcings separately, you could come up with Zurita's conclusions. But if you add them together, all right, where are the 5 warmest years? Easily at the end of the data set. And this shows that our natural variations like ENSO and even multi-decadal oscillations acting in concert can give us the observed temperature records that we see. No need to invoke global warming or statistics. In summary or conclusions, the interannual temperature variations are dominated by ENSO. We shouldn't forget that. Even though we haven't had a strong one in a while, there's a reason. We're back to that period where ENSOs are weak and will be for the next 15 to 20 years. The strength of the ENSO cycle is modulated by other cycles. In the Midwest USA, of course, our research showed that PDO does modulate ENSO cycles in temperature, but we also looked at precipitation as well in Kevin's work. And it's likely that interdecadal and interannual cycles, as forced by natural processes, will be continuing regardless of how the climate changes, and that these things are capable of providing periods of what seem like unusual warmth. Okay, thank you.